We'll be solving the problem, minimum sideways jumps. It is actually a 2D TP problem, only it code. It's a medium level problem, so yeah, we'll be solving this. So basically what is given is there's a 3-lane road n that consists of n plus 1 points, labeled from 0 to n, and the frog starts at point 0 in the second lane and wants to jump to point n, right? So here there's a frog, and this frog wants to jump, like wants to reach the nth position. These are the positions that are represented here. So it wants to go from the position number 0 to position number 4, the end position, right? So it has to go in such a way that it has to avoid the obstacles, right? So in order to avoid the obstacles, it can either go like this or like this or like this. So the frog has 3 options to go. First option is this, second is this, and third is this, right? So you need to actually minimize the number of these sideways jumps which the frog is taking in order to reach from point 0 to point n, right? So yeah, for this, in order to find where we have obstacles, they'll be giving us the obstacles array. So obstacles of I. So here I denotes the position at which the obstacle is there, and this thing, suppose if this is x can be 1, 2 or 3, representing the lane in which we have obstacle at this ith position, right? So now yeah, now initially we know that the frog is already in the second lane, right? So when can this go front? Simple logic. It can only go front if at this position we don't have any obstacle here, right? So suppose let us assume this position is POS, or you can even take it as some IND index. Yeah, so if at index plus 1 there is no obstacle, then it can go front, right? So how do we write this? So if obstacles of index plus 1 is not equal to, yeah, now let us assume you are staying in this lane, and let us denote this lane as a current lane variable, right? So yeah, if obstacles of index plus 1 is not equal to current lane, it means that you can move forward, right? You can move forward. So you will be returning, let us assume that we are representing the recursive function as if, where we take the obstacles array, and the current lane is obviously required, and then the index, of course we need to reach from index 0 to n, right? Yeah, and I forgot to tell you the base case. See, if you have already reached the last position, I mean if the index is equal to n, where n will be the size of the obstacles, if you have already reached there, so what will be the minimum number of sideways jumps that you'll require? 0, right? So you'll simply return a 0. So yeah, what this function represents now, it represents the minimum number of sideways jumps that we require in order to reach from index 0 to index n, right, by avoiding the obstacles. Yeah, so yeah, if the obstacles of index plus 1 is not equal to current lane, I mean we don't have any obstacle in the next position, then we can move forward, right? How do you move forward? By just incrementing the index, right? So you call the function with obstacles, and then you stay in the same lane, right? You're not going any sideways jump, and then just increment the index. Yeah, so this is the case where there is no obstacle in front. What if there is obstacle in front of us? So let us assume you are at position index, and here you have index plus 1, and here you are here, and here you have an obstacle. So you can't go this way, right? You have to either go this way or go this way, right? So how do you choose whether you go this way or this way, right? If there's no obstacle in these sideways, right, then only you can go. So how do you ensure that, right? So how many lanes do we have? 1, 2, and then 3, right? So you will be creating a for loop, like from new lane that you will be jumping into equal to 1, 2 less than equal to 3, right? And now you will be checking that there shouldn't be any obstacle in the new lane that you will be going, right? So if obstacles of, and point to be noted, you are at the same position or the index, you are not incrementing the index, right? At the same index you are moving sideways, right? So if the obstacles of position is not equal to new lane, what does this mean? It means that there is no obstacle in the new lane in which we are about to jump, right? So obstacles of position is not equal to new lane, and the new lane should obviously be not equal to the current lane, right? We are looping from 1 to less than equal to 3. There might be a chance where we'll be encountering a case where the new lane will be equal to the current lane. So just put a basic check condition: the current lane should not be equal to the new lane, right? Yeah, in this case you can actually jump to the sideways, And yeah, if you're jumping, what will be the index value? Index value will be the same, right? Index value will be the same, and this current lane will be the new lane now, right? Obstacles, let me write this here. Yeah, the function would be obstacles comma, new lane comma the same position or the same index, right? Yeah. And yeah, one major point to observe here is that, see, we are at this point, right? What if we have a chance of going here as well as here? But the question is, as you can see the question, it is asking us to return the minimum number of side jumps, right? So you need to minimize the possibilities that you have. You have two possibilities. So when you are computing for each possibility, you need to minimize the possibility every time, right? So how do you do that? Just it's a very simple logic. Just before starting the loop right here, just here you can create a variable. You can create a variable like answer and store it to be a maximum value, like 1 in 9, or you can store it as int max. And whenever your condition is satisfied, and I forgot to tell one thing, yeah, we need to return the minimum number of sideway jumps, right? Here we are taking a jump into the new lane, right? We just need to add +1 here, right? Because it is a jump, right? So if you're moving towards the left or right, you need to include that jump in the answer, right? Yeah. So just initialize the answer to a maximum value, and whenever you found a valid case, then what you need to do is just simply minimize the answer. Answer is equals to minimum of answer comma this entire function call, right? 1 plus f of obstacles new lane and the index, right? So at the end you will be returning your answer, right? Simple logic. Yeah, as it's a recursive solution. Yeah, as it's a recursive solution, it will definitely have some time complexity issues. It will throw you a tail error because at every index there are 3 possibilities to explore. So the time complexity would approximately be equal to 3 power n, where n is the size of obstacles. Yeah. So in order to decrease the time, we can actually use the memoization. So in order to do the memoization, we actually need to observe what are the states of DP that you'll be creating, right? So here there are two things that are changing. The first thing is the index, of course, right? And the second thing is the lane number in which the frog is existing. So this index is going from 0 to n. Current lane can be from 1 to 3, right? So just create a DP, 2D DP array, and of length n+1 you can take, and the current lane would be 4, so that it will be 0 1 2 3. We include these elements. Yeah. So yeah, after the base case, so the base case was okay, or let's write the entire memoized code. Yeah, so the function will be returning an integer which denotes the minimum number of sideway jumps in order to reach the end point. We'll be taking the obstacles array, current lane, and then the index. Yeah, so what was the base case that we discussed? If index is equal to obstacles dot size -1. See, the size of obstacles is n+1, but you will be reaching from index 0 to n. That is the reason we are doing size -1 here. In this case, the number of jumps required will obviously be 0, right? Now, so next case is there is no obstacle in front of us. So if obstacles of index +1 is not equal to current lane, it means that we don't have any obstacle in the next position in the same lane in which we are existing, right? In this case, you'll simply return the same function by incrementing the index. Obstacles, you'll be staying in the same lane and increment the index, right? Yeah. Now what if we have an obstacle in the lane at index +1? So yeah, I told you, initialize the answer to something large like int max, and then initialize the new lane equal to 1. It can be 1 2 or 3, right? So start a loop while new lane less than or equal to 3. What we do is we minimize the answer, right, for every possibility that we find. Minimum of answer comma the jump that we are taking 1 plus f of obstacles, new lane, and index plus 1. So sorry, yeah, here new lane plus plus, yeah. And after the while loop you'll be returning the answer that you got. So this is the entire, the recursive code. Now let's memorize it. So declare it a dp. So yeah, what will be the final function call that you'll be calling? Obstacles, and the current lane is actually 2, because in the question they mentioned that the frog is starting from lane number 2 and the index is 0. This is the final function call that you'll be calling. Yeah, now let's memorize it. So create a 2D dp array, I mean the vector. The size would be n plus 1, where n is the size of obstacles array. It's a very standard traditional thing that we'll be doing in memorization. And then the size of this would be 4, and then fill it with -1. I took 4 because there are 3 lanes, 1 2 3, so yeah. And then here after the base case that you wrote here, if, and don't forget to include the dp array in function call at every time you're calling it dp, and then here also just include dp. Yeah, in the base case, if dp of index and current lane is not equal to -1, simply return dp of index and current lane, right? This is the base case. After the base case, and then here just put dp of index and current lane, and here also. Yeah, so in this way we'll be solving the problem. Thanks for watching.